These are the answers to the AP Chemistry packet that covers topics 4.7 to 4.9. On this slide, you can see Unit 4 at a glance. Unit 4 is entitled Chemical Reactions. In this video, we'll take a look at Topic 4.7, Types of Chemical Reactions, Topic 4.8, Introduction to Acid-Base Reactions, and Topic 4.9, Oxidation-Reduction or Redox Reactions. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Topic 4.7, Types of Chemical Reactions. Here are some essential knowledge statements from the AP Chemistry course and exam description. Acid-base reactions involve transfer of one or more protons between chemical species. Oxidation-reduction reactions, also known as redox reactions, involve transfer of one or more electrons between chemical species, as indicated by changes in oxidation numbers of the involved species. Combustion is an important subclass of oxidation-reduction reactions, in which a species reacts with oxygen gas. In the case of hydrocarbons, carbon dioxide and water are products of complete combustion. In a redox reaction, electrons are transferred from the species that is oxidized to the species that is reduced. Oxidation numbers may be assigned to each of the atoms in the reactants and products. This is often an effective way to identify the oxidized and reduced species in a redox reaction. Precipitation reactions frequently involve mixing ions in aqueous solution to produce an insoluble or sparingly soluble ionic compound. All sodium, potassium, ammonium, and nitrate salts are soluble in water. So we call these the snap ions, the soluble snap ions. So the soluble snap ions that you should know for the AP Chemistry exam, ionic compounds that contain sodium, nitrate, ammonium, or potassium are soluble in water. In a previous packet, you were studying topic 4.2, which is net ionic equations, and you learned the following information about precipitation reactions and how to write equations to represent them. Again, talking about a precipitation reaction, there are three different ways to write a balanced equation for a precipitation reaction: a molecular equation, a complete ionic equation, and a net ionic equation. All right, let's take a look at number 1. For each of the following precipitation reactions, write the molecular equation and the net ionic equation. So for each of these precipitation reactions, we are given the chemical formulas for the reactants, but we have to write the chemical formulas for the products. And then we have to decide which of the products is the precipitate, and then if necessary, we have to balance the equation. All right, let's take a look at the formula for potassium hydroxide, so KOH, and magnesium nitrate, which is Mg, and then with NO3 in parentheses, and there's a 2 on the outside. These are both aqueous, so they're dissolved in water. These are solutions. The formula of potassium hydroxide contains K, which is +1, and OH, which is -1. The formula for magnesium nitrate contains the magnesium ion, which is 2+, and then 2 nitrate ions. Each nitrate is -1. Potassium's new partner to form this product on the other side of the equation would be nitrate. So potassium, K+, NO3 -1, so they go together. So the formula for potassium nitrate is KNO3. And then for magnesium, which is 2+, its new partner is hydroxide. So we need 2 hydroxides for every 1 magnesium so that the charges will balance and cancel out. So our chemical formulas are KNO3 and Mg parentheses OH2. I put question marks since at this point we don't know which of these products is the precipitate. If we take a look at our soluble snap ions, both potassium and nitrate are soluble, so therefore potassium nitrate will be AQ because it's soluble in water, and that means that the precipitate must be the magnesium hydroxide. So there's definitely a precipitate. Once we know which one of the products is soluble, then the other product must be the precipitate. The last thing we have to do for this equation is to balance it. So there are two OHs, two hydroxide ions on the right. So we have to have another potassium hydroxide on the left. And then we need two potassium nitrates on the right. So now the equation is balanced with coefficients from left to right, 2, 1, 2, and 1. Now, moving on to the net ionic equation, first we have to write the complete ionic equation. And so if something is an ionic compound and it's aqueous, then we're going to split it up into separate ions. So 2KOH will be split up into 2 potassium ions and 2 hydroxide ions. Magnesium nitrate will split up into a magnesium ion, which is 2+, and then 2 nitrate ions. On the other side of the equation, because KNO3 is soluble, we're going to split it up into separate ions. So 2KNO3, that splits up into 2 potassium ions and 2 nitrate ions. But now since the magnesium hydroxide is the solid precipitate, we're not going to split that up into separate ions. We just write that as one neutral compound, MgOH2, just like that. Now we cross off the spectator ions that appear in identical form on opposite sides of the equation. So we can cross off the potassium ions, and we can cross off the nitrate ions, and what we have left, what remains, is the net ionic equation. Remember that a correct net ionic equation must be balanced in terms of both atoms and charge. So we have the same number of each type of atom on both sides of the equation, but we also have the overall charge on each side of the equation should be balanced. So there's a total charge of 0 on both the left and the right. Don't forget to include the charges on your ions in the net ionic equation. All right, moving on to our next precipitation reaction. We have silver nitrate, which is AgNO3, and we have sodium carbonate, which is Na2CO3. So the formula for silver nitrate contains a silver ion, so Ag, that's +1, and then nitrate, NO3 -1. The formula for sodium carbonate contains 2 sodium ions and 1 carbonate ion, CO3, which has a charge of 2-. On the other side of the equation, silver is now partnered with carbonate. So we need 2 silvers for every 1 carbonate so that the charges are balanced. That will be Ag2CO3. And then sodium's new partner is nitrate. And since that's +1 and -1, the formula of sodium nitrate is simply NaNO3. Question marks again because we don't know which one of these products is the precipitate. But since sodium and nitrate are soluble, part of the soluble snap ions, that means that sodium nitrate will be soluble, so it gets the AQ, and then the precipitate must be the silver carbonate, the Ag2CO3. To balance the equation, we need 2 silvers on both sides. So we put a 2 in front of the AgNO3, and then we need 2 sodiums and 2 nitrates. So again, the coefficients from left to right in the balanced equation is 2, 1, 1, and 2. All right, moving on from the molecular equation to the complete ionic equation, we're going to split up all of the ionic compounds into separate ions if they are soluble. So silver nitrate, 2AgNO3 splits up into 2 silvers and 2 nitrates. Sodium carbonate splits up into 2 sodium ions and 1 carbonate ion. Again, don't forget to put the charges on your ions. Since silver carbonate, Ag2CO3, is the precipitate, we're not going to split that up, so that just becomes written exactly as you see there. And then 2 NaNO3, that will get split up into 2 Na plus and 2 NO3 minus. Now we cross off the spectator ions on both sides. So we cross off the nitrate ions, we cross off the sodium ions, and then what we have left, what remains, is the net ionic equation. Again, this is balanced in terms of both atoms and charge. Don't forget to put the 2 in front of the Ag as a coefficient. don't forget to put the charges on the ions. Okay, here's our next precipitation reaction. We have solutions of potassium phosphate, so K3PO4, and a solution of calcium nitrate, Ca and then NO3 in parentheses 2. When these combine together, they're going to make a precipitate. The formula for potassium phosphate contains 3 potassium ions for every 1 phosphate ion. Phosphate is PO4, 3 minus. And then calcium nitrate contains 1 calcium ion, which is 2 plus, and 2 nitrate ions, NO3 minus. Potassium's new partner is nitrate, that would be KNO3. And then calcium's new partner is phosphate. But since calcium is 2 plus and phosphate is 3 minus, the least common multiple of 2 and 3 is 6. So to get the charges to balance, we need 3 calcium ions for every 2 phosphate ions. So the correct chemical formula of potassium nitrate is KNO3, and the correct chemical formula for calcium phosphate is Ca3, and then PO4 inside parentheses with a 2 on the outside. Which one of these products is the precipitate? Well, since potassium nitrate is soluble according to the SNAP ions, that means that the precipitate is calcium phosphate. Potassium nitrate is soluble. To balance the equation, we need 3 calciums on the left, and we also need 2 phosphates on the left. So the coefficients from left to right will be 2, 3, and then we'll need enough potassium nitrate ions to balance all those Ks and NO3s. So coefficients would be 2, 3, 6, and 1. That's our molecular equation. Now let's move on to the complete ionic equation. Again, we're going to split up all of the aqueous ionic compounds. So 2 K3PO4, that's going to split up into 6 potassium ions and 2 phosphate ions. 3 CaNO3 parentheses 2, that's going to split up into 3 calcium ions and 6 nitrate ions. 6 potassium nitrates, that'll split up into 6 potassium ions and 6 nitrate ions. And since calcium phosphate, Ca3, and then parentheses PO4 2, that's the precipitate, so we're not going to split that up. We just write that exactly as is. We cross off the spectator ions on both sides of the equation. So we cross off the potassium ions. We cross off the nitrate ions. What remains is our net ionic equation. And notice that this net ionic equation is balanced in terms of both atoms and overall charge. Okay, now we're going to switch from looking at precipitation reactions to looking at acid-base reactions. One of the essential knowledge statements in topic 4.7 says acid-base reactions involve transfer of one or more protons between chemical species. And in topic 4.8, Introduction to Acid-Base Reactions, here are 3 essential knowledge statements. By definition, a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. Only in aqueous solutions, water plays an important role in many acid-base reactions as its molecular structure allows it to accept protons from and donate protons to dissolved species. And when an acid or base ionizes in water, the conjugate acid-base pairs can be identified and their relative strengths compared. All right, let's take a look at the word proton. This is actually the same as referring to the H plus ion. So when referring to acid-base reactions, the term proton and H plus are used interchangeably. So one example of an acid in chemistry is hydrochloric acid, which has the chemical formula HCl. So here is a particle diagram showing an HCl molecule next to a water molecule. Take a look at the proton transfer, or the transfer of the H plus ion. So the HCl loses an H plus ion, and then it gets transferred to the water molecule, forming an ion known as the hydronium ion, which is H3O+. So a proton was transferred from HCl to water in that animation. In addition to hydrochloric acid, which is HCl, there are other substances that are classified as strong acids. And when a strong acid is dissolved in water, it completely ionizes into positive and negative ions. So other strong acids include hydrobromic acid, HBr, hydroiodic acid, HI, perchloric acid, HClO4, nitric acid, HNO3, and sulfuric acid, H2SO4. So according to the Bronsted-Lowry definition of acids and bases, an acid is a proton donor, or an H+ donor, because it donates H+ ions. A base is a proton acceptor, or an H+ acceptor, because it accepts H+ ions. In number 2, it says each of the following reactions is classified as an acid-base reaction because it involves proton transfer. Classify each reactant as either an acid, H+ donor, or a base, H+ acceptor. So HBr is one of the acids I just talked about. H2SO4 is another one of the acids I just talked about. And HNO3, that's hydrobromic, sulfuric, and nitric acid. So the first reactant listed in parts A, B, and C is an acid. And then the second reactant listed, whether it's sodium hydroxide or calcium hydroxide or potassium hydroxide, they all contain the hydroxide ion, which acts as a base. So when the H+ is transferred or donated to the base, the OH- accepts the H+, forming water in each of these reactions. So from the 3 examples shown above, we can make some generalizations about acid-base chemistry, at least from these 3 examples so far. The chemical formula of an acid usually begins with the element hydrogen. The formula of an acid can often be recognized as a partnership between H+ ions and negative ions, such as chloride, Cl-, or bromide, Br-, or nitrate, NO3-, or sulfate, SO4 2-, etc. And a metal hydroxide contains a metal cation, a positive ion, and the hydroxide ion, and these substances are classified as bases because it is the hydroxide ion, the OH-, that acts as a base, a proton acceptor. Okay, now we're going to take a look at some of the interesting properties of water. So in this particular example, we have a chemical reaction, an acid-base reaction between HCl and water. Hydrochloric acid is a compound that is classified as an acid. When HCl dissolves in water, HCl molecules react with water molecules, forming chloride ions and hydronium ions, as represented by the following particle diagram and chemical equation. So HCl is an acid, a proton donor. Ammonia, NH3, is a compound that is classified as a base. When NH3 dissolves in water, the ammonia molecules react with water molecules, forming hydroxide ions and ammonium ions, as represented by the following particle diagram and chemical equation. Ammonia, NH3, is acting as a base, a proton acceptor. So back to the reaction between HCl and water. If HCl is an acid, a proton donor, then in that reaction, that means that water is behaving as a base, as a proton acceptor. And then with the other reaction between water and ammonia, ammonia acts as a base, a proton acceptor, and as we can see here, the water is actually behaving as an acid, as a proton donor. So in number 3, it says, notice that water has the ability to act as either an acid or as a base. Part A, when HCl reacts with water, H2O acts as a base because it accepts a proton. Part B, when NH3 reacts with water, H2O acts as an acid because it donates a proton. Okay, now we're going to talk about conjugate acid-base pairs. So acid-base reactions involve proton transfer from an acid to a base. Some types of acid-base reactions are reversible and can occur in both directions. This is indicated by a pair of double arrows. So what is a conjugate acid-base pair? Well, it's an acid and a base that differ by only a single H+, and these are found on opposite sides of the equation. So in this particular reaction between HCl and H2O, HCl behaves as an acid. So where is the conjugate base of HCl? Well, it's on the other side of the equation. That would be the chloride ion, Cl-. So look closely and you can see that HCl and Cl-, their formulas only differ by a single H+ ion. Water in this reaction is acting as a proton acceptor. So water is a base. Where is the conjugate acid for water? Again, on the opposite side of the equation, that would be the hydronium ion, H3O+. And again, look at the formula for H2O and H3O+. They only differ by a single H+. So they are a conjugate acid-base pair. In the reaction between water and ammonia, water is behaving as an acid, as a proton donor, so the conjugate base of water is on the opposite side of the equation. That would be the hydroxide ion, OH-. H2O, OH- only differ by a single H+, and ammonia, acting as a proton acceptor, as a base, the conjugate acid of ammonia on the opposite side of the equation is the ammonium ion. So NH3, NH4+ are a conjugate acid-base pair. Again, they differ by only a single H+. So now in question 4, it says each of the following substances can act as an acid. Write the correct formula and charge of the conjugate base for each acid. If there is more than one H atom in the formula, remove only one H+ ion to form the conjugate base. So our first example is HF, that's hydrofluoric acid. We're going to remove one H+ ion from that formula. And if the acid is a neutral molecule, then the conjugate base will carry a negative charge, so -1. So there's the fluoride ion, F-. HNO3, or nitric acid, we remove H+, and now we have the nitrate ion, NO3 -1. Even though H2CO3 has two H's in the formula, we are only going to remove one H+ ion to form the conjugate base. So HCO3 with a -1 charge would be the conjugate base. And then same with H2SO4. We take off a single H+ ion, and the conjugate base would be HSO4 with a charge of -1. In our next example, we do not have a neutral molecule. So if the acid happens to be an ion, then we're just going to decrease the charge by 1 unit when we form the conjugate base. So H3O+, we take off an H+, and we end up with H2O. So it has no charge, it's neutral. NH4+, we remove H+, and now we have a neutral molecule, NH3. And if there's a -1 charge, then it becomes -2 to form the conjugate base. So in HCO3-, we remove H+, and now we have CO3, carbonate, with a charge of 2-. And HPO4 already has a 2- charge. We remove the H+, and now we go from 2- to 3-. So we form the phosphate ion, which is PO4 3-. So all of those formulas have the correct formula and charge. Those are the conjugate base for that corresponding acid. Okay, now we're going to switch it around. So instead of removing an H+ ion, now we are going to add an H+ ion. Okay, this is question 5. Each of the following substances can act as a base. Fill in the missing information in the table below by writing the correct formula and charge of the conjugate acid. Add only one H+ ion to form the conjugate acid. So when we add one H+ ion, if the base is a neutral molecule, then the conjugate acid will have a 1+ charge. So NH3 becomes NH4 with a charge of +1. ClO minus becomes HClO. If the base is an ion, we're going to simply increase the charge by 1 unit. So HClO has no charge. We go from -1 to 0. NO2 minus, that's going to become a neutral molecule, HNO2, with no charge. OH minus, hydroxide, the conjugate acid would be the neutral water molecule, H2O. And now HCO3 becomes H2CO3. Again, no charge because it was -1 and now it's 0. Well, what if it's -2? So S2 minus. If we add a single H, now the charge goes from 2 minus to 1 minus. So HS has a charge of -1. HSO3 has a charge of -1. We go from 2 minus to 1 minus. And then phosphate, PO4, that's a charge of 3 minus. So we go from 3 minus to 2 minus. And so I write the conjugate acid as HPO4 with a charge of 2 minus. So each of those substances, that's the correct formula and charge for the conjugate acid. Okay, now that you understand how to write the formula for either a conjugate base or a conjugate acid, let's take a look at an acid-base equation and see if we can recognize two sets of conjugate acid-base pairs. So in this particular acid-base reaction, HNO2 and NO2 minus represent one of the conjugate acid-base pairs. Again, they only differ by a single H plus. And then the other conjugate acid-base pair would be H3O plus and H2O. All right, this is number 6. Identify both sets of conjugate acid-base pairs in the reaction above. So I see CH3, CH2, COOH on the left. That's going to behave as an acid. And when the H plus or the proton is removed from that molecule, we get the conjugate base, which is CH3, CH2, COO minus. The other conjugate acid-base pair would be water. And when H plus is added, we form the hydronium ion. So H3O plus and H2O represent the other conjugate acid-base pairs. All right, looking at number 7, it's the same kind of process. So here is question 7. On the left, I see CH3, CH2, NH2. So what happened is the proton was added, and so its conjugate acid would be CH3, CH2, NH3 plus. Again, those two are only different by a single H plus ion. And then the other conjugate acid-base pair is water and the hydroxide ion. Okay, now we're going to transition from acid-base reactions to oxidation-reduction reactions. So in topic 4.7, I had already mentioned these earlier in the video, but I'll go ahead and mention them again. This has to do with oxidation-reduction reactions, also known as redox reactions. They involve the transfer of one or more electrons between chemical species, as indicated by changes in oxidation numbers of the involved species. Combustion is an important subclass of oxidation-reduction reactions in which a species reacts with oxygen gas. And in the case of hydrocarbons, carbon dioxide and water are products of complete combustion. In a redox reaction, electrons are transferred from the species that is oxidized to the species that is reduced. Oxidation numbers may be assigned to each of the atoms in the reactants and products. This is often an effective way to identify the oxidized and reduced species in a redox reaction. So again, topic 4.9, oxidation reduction or redox reactions. Balanced chemical equations for redox reactions can be constructed from half reactions. Okay, what you will see in your packet, and you can see here on this slide, is a QR code that will take you to a video in which a piece of magnesium is burned in air. A bright light is released, and the chemical reaction is magnesium reacting with oxygen to form the ionic solid magnesium oxide. I can put a link to this particular video in the video description area. The balanced chemical equation for the reaction between magnesium and oxygen is shown below. So 2 moles of magnesium solid react with 1 mole of oxygen gas to produce 2 moles of magnesium oxide solid. The magnesium oxide contains magnesium ions, so Mg2+, and oxide ions, O2-. And the equation shown above can be split up into 2 separate processes. An atom of magnesium changes into a magnesium 2+ ion, and a molecule of O2 changes into 2 oxide ions. So oxidation involves the loss of electrons, and reduction involves the gain of electrons. And you can use the mnemonic device oil rig to help you remember that oxidation is the loss of electrons and reduction is the gain of electrons. Equations that show either oxidation or reduction separately are known as half reactions. So now we have the oxidation half reaction for magnesium. Electrons are lost and they appear on the right side of the equation. So Mg changes to Mg2+ plus 2 electrons. And in a reduction half reaction, electrons are gained and they appear on the left side of the equation. So here we have O2 plus 4 electrons and it produces 2 oxide ions. A half reaction should be balanced in terms of both atoms and charge. The number of electrons lost in the oxidation half reaction must be equal to the number of electrons gained in the reduction half reaction. So you may need to multiply a half reaction by a certain number so that the electrons can be canceled out on both sides of the equation when you add the 2 half reactions together. So if you do that, the result is the overall balanced redox equation. Again, it should be balanced in terms of both atoms and charge. So the magnesium half reaction was multiplied by 2 so that the electrons that are gained in the reduction are equal to the electrons lost in the oxidation. So the electrons cancel out on both sides, and now we have 2 Mg plus O2, and it makes 2 MgO, because again, we're combining the magnesium and the oxide to make that ionic solid, magnesium oxide. So electrons are canceled out on both sides, and they do not appear in the overall redox equation. Okay, let's take a look at question 8. It says, explain why the equation above is not completely balanced. So if we look closely, we realize that we have aluminum, which is an atom, but then we have a copper ion on the left. And on the right, we have a copper atom and an aluminum ion. So looking at those charges, they're not the same on both sides of the equation. We have a total charge of +2 on the left, and we have a total charge of +3 on the right. Remember that a redox equation should be balanced in terms of both atoms and charge. So we're going to split up this reaction into 2 separate half reactions. So for the aluminum half reaction, that would be oxidation. Remember, oil rig, oxidation is the loss of electrons. So I put 3 electrons on the right to balance the charge. And then reduction is the gain of electrons. So for the copper half reaction, I'm going to put 2 electrons on the left. Again, I'm trying to balance the overall charge. Now, when I add the 2 half reactions together, I need the electrons to get canceled out. And the least common multiple of 2 and 3 is 6. So to get 6 electrons on both sides, I'm going to multiply the aluminum half reaction by 2. And I'll multiply the copper half reaction by 3. And when I do that, I will have 6 electrons on opposite sides. So I can cancel them out. And now, when I add the 2 half reactions together, this is what I get. I have 2 aluminums and 3 copper ions. I have 2 aluminum ions and 3 copper atoms. So in terms of charge, I have a total charge of +6 on both the left and the right. So this now is the overall balanced redox equation, and it's balanced in terms of both atoms and charge. All right, let's move on to question 9. In each of the following examples, add the 2 half reactions together to produce a balanced redox equation in which the electrons are canceled out on both sides. So in part A, we have an oxidation half reaction that has 1 electron on the right, and we have a reduction half reaction with 5 electrons on the left. So let's multiply the oxidation half reaction by 5. And when we do this, now we can add the two half reactions together. So the electrons will cancel out on opposite sides. So 5 electrons on the left, 5 electrons on the right. And this should be our overall balanced equation. But let's just double check that the charge is balanced on both sides of the equation. So let's take a look at each of the components on the left and the right. 5 times positive 2 is positive 10. Then we have a polyatomic ion that carries a charge of negative 1. And then 8 times positive 1 is positive 8. On the other side of the equation, 5 times positive 3 is positive 15. We have a monoatomic ion that carries a charge of positive 2. And then we have water, which is neutral and has no charge. So on the left, it would be negative 1 plus 10 plus 8. That's positive 17. And on the right, we have positive 15 and positive 2. So there is a total charge of positive 17 on both sides of the equation. So this is the balanced redox equation. All right, let's take a look at part B. We have an oxidation half reaction with 2 electrons on the right and a reduction half reaction with 6 electrons on the left. So let's multiply the oxidation half reaction by 3. And when we do this, now we can get the electrons to cancel when we add the two half reactions together. So there's 6 electrons on opposite sides of the equation. This is our overall equation. Let's double check and see that it's balanced. 6 times negative 1 is negative 6. 14 times positive 1 is positive 14. And we have a polyatomic ion that carries a charge of negative 2. On the other side of the equation, we have neutral molecules of chlorine and water, and 2 times positive 3 is positive 6. So negative 6 plus 14 minus 2, that's going to give us a positive 6 on both the left and the right. So the charge is balanced. This is the overall balanced redox equation. All right, moving on to part C. We have an oxidation half reaction with 2 electrons on the right and a reduction half reaction with 3 electrons on the left. Since the least common multiple of 2 and 3 is 6, let's multiply the oxidation half reaction by 3, and we'll multiply the reduction half reaction by 2. When we do this, and we add the two half reactions together, the electrons will cancel out on opposite sides. So this is our overall equation. Let's just double check that the charge is balanced. 3 atoms of nickel, so no charge. 8 times positive 1 is positive 8. 2 nitrate ions would be 2 times negative 1, so negative 2. 3 times positive 2, positive 6. And then we have neutral molecules of NO and H2O. So if we look at the total charge on the left and the total charge on the right, 8 minus 2 is positive 6. So there's a total charge of positive 6 on both the left and the right. So this is the overall balanced redox equation. All right, now we're going to take a look at some rules for assigning oxidation numbers. In a redox reaction, electrons are transferred from the substance that is oxidized to the substance that is reduced. One of the ways to recognize a redox reaction is to look for changes in oxidation numbers. Oxidation numbers are assigned to elements according to the following rules. Number 1, if an atom is in its elemental form, the oxidation number is 0. And you can see examples of hydrogen, lithium, nitrogen, carbon, chlorine, and iron. There's no charge. These are just elements, so the oxidation number is 0 for all of these examples. Number 2, the oxidation number of a monoatomic ion is the charge on that ion. So each of these examples, we have a +1 or a +2 or a +3 or a -1, -2, -3. The charge on that ion is the oxidation number. Number 3, the oxidation number of a metal in group 1 is +1 in all compounds. So in the example, I have sodium, which is +1 in compounds such as NaCl, NaNO3, Na2CO3. And the oxidation number of a metal in group 2 is +2 in all compounds. And here's an example of magnesium, which has an oxidation number of +2 in compounds such as MgBr2, MgSO4, and MgO. Number 4, the oxidation number of fluorine is -1 in all compounds. So because fluorine is so electronegative, then in all of the compounds, here's an example of NaF, CH3F, SF2, the oxidation number of fluorine is -1 in all compounds. Number 5, the oxidation number of hydrogen is usually +1 when hydrogen is bonded to nonmetals. And here's an example where H2O, CH3OH, NH4Cl, H2S, hydrogen carries an oxidation number of +1 in those compounds because it's bonded to nonmetals. But then hydrogen is -1 when bonded to metals. So examples of lithium hydride, so LiH, NaH, CaH2, hydrogen carries an oxidation number of -1 in these compounds because it's bonded to a metal. Number 6, the oxidation number of oxygen is usually -2 in most ionic and molecular compounds. So here I'm showing Na3PO4, that's an ionic compound, Mg and then NO3 parentheses 2, again sodium phosphate, magnesium nitrate, those are ionic compounds. And in most molecular compounds such as CO2, H2SO3, N2O, P2O5. So oxygen carries an oxidation number of -2 in these compounds. But two important exceptions to this rule are hydrogen peroxide, H2O2, where oxygen carries an oxidation number of -1, and then oxygen difluoride. Since fluorine is -1 in all compounds, that would make oxygen +2. So oxygen is usually -2 in most compounds, but there are two important exceptions to this rule. And then the last rule here is rule number 7, the oxidation number of the halogens. So that would be in the column 17 on the periodic table. So below fluorine, chlorine, bromine, and iodine. The oxidation number of these halogens is -1 in most binary compounds that contain only 2 elements. So examples of KCl, NaBr, MgI2, CCl4, SBr2, HI. Oxidation number of the halogen would be -1. But when chlorine, bromine, and iodine are bonded with oxygen or with fluorine, they will have a positive oxidation number. So here I'm showing that chlorine in compounds such as NaClO and HClO, chlorine would carry an oxidation number of +1. Chlorine carries a +3 oxidation number in a compound NaClO2 or HClO2, and then chlorine can be +5 or +7. So we'll take a look at examples of assigning oxidation numbers to an element in various compounds. All right, I think these rules will make more sense to you when you see more examples. Just one last thing to mention before we take a look at number 10. The sum of the oxidation numbers of all atoms in a neutral compound is 0. So, for example, if we have CH4, I know that hydrogen normally carries an oxidation number of +1 when it's bonded to nonmetals, such as carbon. And we have 4 hydrogen atoms in this compound. So the oxidation number of the carbon is unknown, but when I add them together, it should equal 0. So if I have +1 times 4, that's 4. Therefore, the carbon has an oxidation number of -4, so that when I add these two numbers together, I get 0. The sum of the oxidation numbers of all atoms in a polyatomic ion is equal to the overall charge of the polyatomic ion. So in this case, the carbonate ion carries a charge of -2. I have oxygen, which is normally -2 in most compounds. We have 3 of them. So that would be -6. The carbon is unknown at the moment, but when I add these together, I should get -2 overall. So therefore, the carbon would carry an oxidation number of +4 because +4 plus -6 equals -2. And then before we move on to number 10, just a final warning to be careful not to make the following mistake. So for example, CH4, carbon was -4, hydrogen was +1. Be careful not to group the entire atoms. Hydrogen does not carry an oxidation number of +4, it's +1. So we're assigning the oxidation number to an individual atom in a chemical formula. In our next example with sulfur dioxide, the oxygen is -2. Just because you have two oxygens, you don't assign an oxidation number of -4 to the oxygen. So it's individual atoms. And in that last example of sodium carbonate Na2CO3, the sodium is +1, the carbon is +4, the oxygen is -2. So don't assign sodium +2 because you're grouping all the sodiums together. Don't assign an oxidation number of -6 to oxygen. It's what is the oxidation number of an individual atom in a chemical formula. All right, this is question 10. I know we have a lot of oxidation numbers to assign, but I will do my best to explain using the rules that I already mentioned. So our first set, iron, chlorine, phosphorus, these are elements. So in their elemental form, the oxidation number would be 0 for these elements. In our next set of compounds, these are all ionic compounds. They consist of a metal and a nonmetal. And the oxidation number of a metal in group 1, like sodium, is +1. So therefore, the bromine would have to be -1. And that's the normal charge you would expect on the monoatomic ion, bromine. Calcium is in group 2, so its oxidation number is normally +2. And then there are 3 calciums. So 3 times +2 is +6. We have 2 nitrogens. Each nitrogen is worth -3. And again, that is the normal charge you would expect on the monoatomic nitrogen ion. Magnesium is also in group 2, so it should be +2. We have 1 sulfur, so sulfur would be -2. And again, that's the normal charge you would expect on the sulfide ion. Oxygen as an ion is normally -2. So the oxidation number of a monoatomic ion is the charge on that ion. Iron would be +3 in this example because we have 3 oxygens, so altogether that would be -6, and we have 2 irons, so each iron is worth +3. All right, in our next example, we have sulfur dioxide. Oxidation number of oxygen is normally -2 in most ionic and molecular compounds. So sulfur would be +4 in the sulfur dioxide molecule. Again, we're trying to get the oxidation numbers to add up to equal 0 for a neutral compound. These next 2 compounds contain carbon, hydrogen, and fluorine. The oxidation number of fluorine is -1 in all compounds. Hydrogen is normally +1 when bonded to a nonmetal such as carbon. So the carbon in this example would be -2. And in the next example, fluorine is still -1. Hydrogen is still +1. Now the carbon is actually +2. Let's take a closer look at how the carbon changes from -2 to +2 in these 2 compounds. All right, so CH3F. Carbon is unknown, that's why I put a question mark. Hydrogen is +1, and we have 3 of them. And fluorine is -1, and we have only 1 fluorine. But the sum of the oxidation numbers should equal 0. If I do the math, +3, -1, that would be a +2. That would force the carbon to, in this case, be -2 so that the sum of the oxidation numbers is equal to 0. I'm just trying to work out the math to help you see where that -2 comes from. In the other example, it was CHF3, so we have 1 hydrogen, which is +1. We have 3 fluorines. Each fluorine is worth -1. So if we do that math, +1, -3, That's -2. That would force the carbon in this example to be +2, so that the sum of the oxidation numbers equals 0. Well, hopefully that helps you see where those oxidation numbers were coming from for the carbon. Let's move on to our next example. Oxidation number of oxygen is usually -2 in most ionic and molecular compounds. So I have carbon monoxide. Well, if O is -2, that means that carbon would be +2 in that compound. And now we come to oxygen difluoride, OF2. Fluorine is always -1, but that's going to force the oxygen to be +2 so that the sum of the oxidation numbers is equal to 0. That was one of the exceptions that I mentioned. And here's another exception. If hydrogen is +1 when bonded to nonmetals, in hydrogen peroxide, H2O2, that's going to force the oxygen to be -1. So again, those were the exceptions that I mentioned, hydrogen peroxide and oxygen difluoride. In our next two examples here, we have a metal bonded to hydrogen. So remember, when hydrogen is bonded to a metal, it's going to carry an oxidation number of -1. Potassium is in group 1, so that should be +1. That's going to make hydrogen -1. Calcium is in group 2, so calcium is +2, and that's going to make, again, the hydrogen -1. Hydrogen is bonded to metals, it's going to be -1. In our next set of compounds, we have HBr, and then HBrO, HBrO2, HBrO3. So what's going to happen is the bromine is going to change its oxidation number as we kind of move down this set. Hydrogen is normally +1 when bonded to nonmetals. Oxygen is normally -2 in most ionic and molecular compounds. So let me go ahead and fill in the oxidation number for hydrogen and oxygen in this set of 4 compounds. Now, in the first example, HBr, if H is +1, bromine would have to be -1. So the oxidation number of the halogens is usually -1 in most binary compounds that contain only 2 elements. But when a halogen, such as bromine, is bonded with oxygen or fluorine, it's going to have a positive oxidation number. So what's the oxidation number of bromine in these next 3 compounds? Well, it's going to be +1, +3, and +5. Let me go ahead and work out why is the bromine +1, +3, and +5. Let me break this down. So here's HBrO. If H is +1 and O is -2, and bromine is whatever it needs to be so that the sum of the oxidation numbers is equal to 0, hopefully you can see that a +1 and a -2, when added together, gives you -1, and that forces the bromine to be +1, so that the sum of the oxidation numbers is equal to 0. Well, if I have HBrO2, now I have 2 oxygens. Again, hydrogen is still +1. Oxygen is -2, but we have 2 of them. So that's +1 and -4. When I add those together, I get -3. That's going to make the bromine equal to an oxidation number of +3, so that the sum overall of the oxidation numbers is equal to 0. And then in that other example where I have HBrO3, again, 3 oxygens, each of them is worth -2. I have 1 hydrogen, which is +1, so +1 and -6 would be -5. That makes the bromine have an oxidation number of +5. So I was just trying to work out where those oxidation numbers for bromine were coming from. Hopefully that helps. And now moving on to our next set of compounds, we have Na2CO3 and BaCrO4. Well, the sodium is in group 1, so it's +1. The oxygen is normally -2. Again, barium is in group 2, so that's +2. Okay, so oxygen is normally -2. Now, what is the carbon's oxidation number? It's going to be +4. And then for chromium, Cr, it's going to be +6. Let me go ahead and work those out for you to kind of explain where those numbers are coming from. So here's Na2CO3. We have sodium is +1, and we have 2 of them. Oxygen is -2, and we have 3 of them. So if I do the math and then let the carbon be whatever it needs to be so that the sum of the oxidation numbers is 0, I have a +2, a -6, that would be -4. Hopefully you can see why the carbon would have to be +4 in Na2CO3. I was just trying to work out the math to explain that. And then that other compound was barium CrO4, so BaCrO4. If barium is +2 and oxygen is -2, but we have 4 of them, I've got a +2, a -8. Chromium is whatever it needs to be so that the sum of the oxidation numbers is 0. So barium +2, oxygen -2. We have 4 of them. That's +2 and -8 is -6. So chromium would have to be +6. Hopefully you can see how that math works out. All right, so we're almost done with this set. Now we have a bunch of polyatomic ions to assign. I'm going to go ahead and fill in automatically. Hydrogen is +1. Oxygen is -2, so there's nothing weird or no exceptions to the rule there. So I've already filled in the oxidation number of hydrogen and oxygen. Now let's figure out what the rest of the oxidation numbers are. So -3 for nitrogen in the NH4 plus ion, +5 for the nitrogen in the nitrate ion, NO3 minus. Chlorine in this particular polyatomic ion, ClO4 minus, would be +7. In these next examples, the sulfur SO3 2 minus, sulfur would be +4. SO4 2 minus, sulfur would be +6. Cr2O7 carries an overall charge of -2. The chromium would be +6 in that ion. Phosphate, PO4 3 minus, phosphorus would be +5. Now, I'm not going to work out every single example, but let's take a look at a few examples just to help you understand where those oxidation numbers are coming from. So here's the NH4 plus. Remember that the sum of the oxidation numbers in a polyatomic ion is equal to the overall charge on that polyatomic ion. So if I have 4 hydrogens, each hydrogen is worth +1, that would be +4. The nitrogen would have to be -3 so that when I add them together, I get a +1 overall. In the NO3 minus, or the nitrate ion, I have 3 oxygens. Each oxygen is worth -2. I have 3 of them, that's -6. The nitrogen would have to be +5 so that when the sum of the oxidation numbers overall is equal to -1. That's the charge on the nitrate ion. Here's the ClO4 minus ion. This is called perchlorate. I have 4 oxygens. Each oxygen is worth -2. So that's -8. The chlorine would have to be +7 so that when I add the oxidation numbers together, I get -1, which is the overall charge on that ion. And here, this particular ion is Cr2O7. This is the dichromate ion. It carries an overall charge of -2. I have 7 oxygens. Each oxygen is worth -2, so that would be -14. I have 2 chromiums, so collectively, the 2 chromiums together would be +12, but each chromium is worth +6. Remember, we assign an oxidation number to an individual atom in a compound or a polyatomic ion. All right, well, hopefully that was helpful in terms of assigning oxidation numbers and learning the rules and the application of those rules in number 10. All right, we're now ready to move on to question 11. The nice thing about question 11 is it gives you the chance to practice your skills in assigning oxidation numbers to different elements. So here we have to assign the oxidation numbers to each element on each side of the equation, and then determine which element is oxidized and which element is reduced. So on the left side of the equation, we have an iron nitrate compound, and there are 2 nitrate ions for every 1 iron. So each nitrate is worth -1. that means that since we have two of them, the charge on the iron is +2. So the oxidation number of iron is +2. Aluminum is in elemental form. That's going to be an oxidation number of 0. And then within the nitrate, oxygen happens to be -2, and nitrogen is +5. And we've already seen nitrate as an example in question 10. On the other side of the equation, now iron is in elemental form, so that would be 0. We still have the nitrate ion, so that's still going to be +5 and -2 for those elements, nitrogen and oxygen. And now the aluminum is paired up with 3 nitrate ions, so therefore the charge on the aluminum ion would be +3. All right, let's see what changes. Well, the iron changes from +2 to 0, and if the oxidation number decreases, the element is reduced. So iron is reduced from +2 to 0. Aluminum is changing from 0 to +3, and if the oxidation number increases, the element is oxidized. So aluminum is being oxidized from 0 to +3. In our next example, on the left side of the equation, oxygen is -2, hydrogen is +1, and based on the skills that you have learned in assigning oxidation numbers, we're going to get a +5 for the bromine, and we're going to get a -2 for the nitrogen. On the other side of the equation, bromine is -1 as a monoatomic ion. Oxygen is -2. Nitrogen is in elemental form, so it's 0, and then hydrogen is +1. Let's see what's changing. So bromine is changing from +5 to -1. If the oxidation number decreases, the element is reduced. So bromine is being reduced from +5 to -1. Nitrogen is changing from -2 to 0. So if the oxidation number increases, the element is oxidized. So nitrogen is oxidized from -2 to 0. In our next example, we have phosphorus in elemental form. So that's going to be 0. Hydrogen is +1. Oxygen is -2. And the chlorine in that HClO compound, chlorine carries an oxidation number of +1. On the other side of the equation, hydrogen is +1. Oxygen is -2. In the H3PO4 compound, phosphorus would be +5. And in the HCl compound, chlorine is -1. Let's see what's changing. So phosphorus changes from 0 to +5. The oxidation number is increasing. So phosphorus is being oxidized from 0 to +5. Chlorine is changing from +1 to -1. So its oxidation number is decreasing. So chlorine is being reduced from +1 to -1. In our next example, hydrogen is +1. In the C2H6 compound, carbon would be -3. And then oxygen is in elemental form, so it's going to be 0. On the other side of the equation, hydrogen is +1. Oxygen is -2. In carbon dioxide, carbon is +4. Let's see what's changing. Carbon is changing from -3 to +4. That oxidation number is increasing. So carbon is being oxidized from -3 to +4. Oxygen is being reduced from 0 to -2. All right, here's our last example. We have manganese in elemental form, so it's 0. Hydrogen is +1. Oxygen is -2. And in the H2SO4 compound, sulfur is +6. On the other side of the equation, we have MnSO4, and the charge on the sulfate ion is -2. That makes the manganese ion +2. So manganese is +2. Hydrogen is in elemental form, so it's going to be 0. And within the sulfate ion, oxygen is -2, sulfur is +6. All right, let's take a look and see what's changing. Manganese is changing from 0 to +2, so it's being oxidized from 0 to +2. And hydrogen is being reduced from +1 to 0. All right, let's move on to question 12. So what we have to do in number 12 is to classify each of the following reactions as precipitation, acid-base, or redox. Here is a reminder of the essential knowledge statements for topic 4.7, types of chemical reactions. So acid-base reactions involve the transfer of protons. Oxidation-reduction or redox involves changes in oxidation number. And precipitation reactions involve combining aqueous solutions to produce a solid precipitate. So looking at these 6 reactions, do I see an example where aqueous solutions are combined to form a solid precipitate? Well, in that third example, I see aqueous solutions of silver nitrate and hydrochloric acid to make solid silver chloride. So that's a precipitation reaction. And then another example where aqueous solutions are combined to make a solid precipitate would be the 5th example. We have solutions of lead nitrate and potassium sulfate to produce a precipitate of lead sulfate. All right, as far as the other types of reactions, we're looking for either acid-base or redox. Remember that an acid-base reaction involves proton transfer, so H+ being transferred from the acid to the base. Common examples of acids include HBr, H2SO4, HNO3, and metal hydroxides are good examples of bases that contain the hydroxide ion as a proton acceptor. So do we see any combinations of H+ and OH- to make water? Well, calcium hydroxide is a metal hydroxide, that's a base. Hydrochloric acid contains H+, that's an acid. We're making water. That is an acid-base reaction. Another example where we have a metal hydroxide, so potassium hydroxide is base. Sulfuric acid is the acid. H+ and OH- combine to make water. So that is also an acid-base reaction. And then the remaining 2 reactions are classified as redox. Let's take a closer look. Why is the first reaction redox? Well, zinc is changing from an oxidation number of 0 to +2. So zinc is being oxidized from 0 to +2. And then hydrogen is being reduced from +1 to 0. So that's a redox. And in that last example, we have lead, which is +2 on both sides of the equation, so that's not changing. Hydrogen is +1 on both sides of the equation, so that's not changing. But sulfur is changing from -2 to +6. So sulfur is being oxidized. And then the oxygen in hydrogen peroxide is -1, and it's changing to -2. So oxygen is being reduced from -1 to -2. All right, well, that takes care of question 12. Let's move on to the last question in the packet, question 13. In each of these examples, in question 13, we have to write the balanced net ionic equation. And so the question we have to ask ourselves is, do I split up the formula into separate ions, or do I leave it unchanged? So if you see a substance that is a gas, or a pure liquid like water, or a solid, or if you see something that you know is a covalent or molecular substance that would exist in the form of molecules, then you don't split it up. You leave it unchanged. However, if you see an aqueous ionic compound that contains positive and negative ions, or a metal and a nonmetal, or you see one of the 6 strong acids, then you would split that up into separate ions. Okay, let's take a look at part A. The first substance I see is calcium, but it's a solid, so we're not going to change it, just write it exactly as is. Then I see hydrochloric acid. So that is one of the 6 strong acids. So then we are going to split it up. And when we do, with the coefficient of 2, it becomes 2H plus and 2Cl minus. On the other side of the equation, I see an aqueous ionic compound. So calcium chloride is an ionic compound. And we split it up into a calcium 2 plus ion and 2 Cl minus ions. And then finally, hydrogen is a covalent molecular compound. It's a gas, so no change. We're not going to split that up at all. On the left and the right, I see chloride ions, so we can cross off the chloride ions as spectator ions. And then what remains is our net ionic equation. All right, moving on to part B. The first thing I see is iron. It's a solid, so we're not going to change it, so leave it as is. Hydrobromic acid is one of the 6 strong acids, so we split that up, and there's a 6 in front of the HBr. So when we split this up into ions, it's going to be 6H plus and 6Br minus. On the other side of the equation, the iron bromide compound is a aqueous ionic compound, so we are going to split that up, and there's a 2 in front. So we have 2 Fe 3 plus ions and 6 Br minus ions. Hydrogen is a molecular compound. It's a gas. We're not going to change it or split it up. So I see the Br minus ions on opposite sides of the equation, so we can cross off those spectator ions. And then what we have, what remains, is now the net ionic equation. All right, moving on to part C. Zinc solid, not going to split it up, not going to change it, so just exactly as is. Nickel nitrate is a aqueous ionic compound, so it's going to be 1 nickel with a charge of 2 plus, and then 2 nitrate ions. On the other side of the equation, we're going to split up the zinc nitrate, which is also an aqueous ionic compound. So it splits up into zinc 2 plus, and again, 2 nitrate ions. And then nickel solid, we're not going to change it, just solid exactly as is. Let's cross off those nitrate ions on opposite sides of the equation, and then what remains is now our net ionic equation. Moving on to part D. Aluminum is a solid, so we leave it as is. Silver nitrate is an aqueous ionic compound, and there's a 3 in front, so it's going to split up into 3 silver plus ions and 3 nitrate, NO3 minus ions. We split up aluminum nitrate as an aqueous ionic compound, so it's going to be aluminum 3 plus and 3 nitrate ions. Each nitrate is -1. And then silver solid is going to just be remaining as is, no change. Let's cross off those nitrate ions on both sides of the equation, and then what we have left is our net ionic equation. All right, moving on to part E. Copper solid, just leave it as is, no change. Nitric acid, HNO3, is one of our 6 strong acids, so we are going to split it up. There's a 4 in front, so it's going to split up into 4H plus and 4 NO3 minus ions. We're going to split up copper nitrate into a copper 2 plus ion and 2 nitrate ions. And since water and NO2 are molecular compounds, pure liquid and a gas, they're covalent, they exist as molecules, no change. So we leave them as is. Let's cross off the nitrate ions on both sides, but we have 4 nitrate ions on the left, and we have only 2 nitrate ions on the right. So we can't cross off all the nitrate ions, but we do change that coefficient on the left from a 4 to a 2. So there is a net 2 nitrate ions on the left. And again, that now becomes our final answer for our net ionic equation. All of these net ionic equations are balanced in terms of both atoms and charge. Okay, let's move on to part F. The first thing I see is Br2. That's a molecule, that's an element. We're not going to change it at all. Then I see an aqueous ionic compound. So potassium iodide will be split up, and because there's a 2 in front, it'll split up into 2K plus and 2I minus. And on the other side of the equation, we have another aqueous ionic compound, so potassium bromide. Again, because of that 2 in front, it's going to split up into 2K plus and 2Br minus. And then finally, the molecule I2, that's covalent. We're not going to split that up at all, so no change. Once we cross off the potassium ions as spectator ions on both sides of the equation, what we are left with is our net ionic equation. So that was the end of the question 13. It's also the end of this packet. So I hope that the answers and explanations were helpful. Thanks for watching.